COMMUNICATINCOMMUNICATIONSYSTEMSLAB. 1. Implementation of RF oscillators. Experiment No. 1. Implementation of RF oscillators. Page 1. Objectives. To understand the basic theory of oscillators. To design and implement the Colpitts, Hartley and 555 oscillator. To practically measure the output frequency of Colpitts, Hartley and 555 oscillator. Equipment required. DMM. Oscilloscope. DC power supply, plus 12 volts, fixed plus 5 volts, fixed, resistors 22k omega, QTY equals 1, 10k omega, QTY equals 1, 2.2-k omega, QTY equals 1, 2k omega, QTY equals 1, 1k omega, QTY equals 1, capacitors, 0.01 UF QTY equals 1, 0.1 UF QTY equals 1, 1 UF QTY equals 1, 10 UF QTY equals 4, inductor, 27 QTY equals 1, 1 mH QTY equals 1, 2.2-mH QTY equals 1, transistor, NPN BJT 2N3904, QTY equals 1, IC, 555 timer, QTY equals 1, connecting wires. Theory. An oscillator is an electronic circuit, which generates periodic signal on its output without the necessity of an input signal. Oscillators are widely used in most communications systems as well as some digital systems, including computers, to generate required frequencies and timing signals. In addition, oscillators are found in many types of softest instruments like those used in the laboratories. Oscillators produce various types of outputs including sine waves, square waves, triangular waves, and sawtooth waves. The output voltage can be at the sinusoidal or in sinusoidal. Depending on the type of oscillator, the sinusoidal oscillator operation is based on the principle of positive feedback, where a portion of the output signal is fed back to the input in a way that causes it to reinforce itself and thus sustain a continuous output signal. Oscillators are often characterized by the frequency of their output signal, a low-frequency oscillator, LFO. Is an electronic oscillator that generates a frequency below approximately 20 Hz. This term is typically used in the field of audio synthesizers to distinguish it from an audio frequency oscillator. An audio oscillator produces frequencies in the range about 16 Hz to 20 kHz. An RF oscillator produces signals in the radio frequency RF range of about 100 kHz to 100 GHz. Experiment No. 1. Implementation of RF oscillators. Page 2. Depending upon the circuitry, there are two major types of oscillators: feedback and relaxation oscillators. Essentially, an oscillator converts electrical energy from the DC power supply to periodic waveforms. A basic oscillator is shown in Figure 1.1. Figure 1.1. Basic concept of an oscillator. One type of oscillator is the feedback oscillator, which returns a fraction of the output signal to the input with no net phase shift, resulting in a reinforcement of the output signal after oscillations are started. The loop gain is maintained at unity. 1. To maintain oscillations, a feedback oscillator consists of an amplifier organ, either a discrete transistor or an op-amp, and a positive feedback circuit that produces phase shift and provides attenuation, Arsanen. Figure 1.2. Figure 1.2. Concept of a feedback oscillator. A second type of oscillator is the relaxation oscillator. Instead of feedback, a relaxation oscillator uses an RC timing circuit to generate a waveform that is generally a square wave or other sinusoidal waveform. Typically, a relaxation oscillator assesses a Schmitt trigger or other device that changes states to alternately charge and discharge a capacitor through a resistor. Experiment No. 1. Implementation of RF oscillators. Page 3. Feedback oscillator. Feedback oscillator operation is based on the principle of positive feedback. Feedback oscillators are widely used to generate sinusoidal waveforms. Positive feedback is characterized by the condition wherein a portion of the output voltage of an amplifier is fed back to the input with no net phase shift, resulting in a reinforcement of the output signal. This basic idea is illustrated in Figure 1.3. Figure 1.3. As you can see, the in-phase feedback voltage, VF, is amplified to produce the output voltage, which in turn produces the feedback voltage. That is, a loop is created in which the signal sustains itself and a continuous sinusoidal output is produced. This phenomenon is called oscillation in some types of amplifiers. The feedback circuit shifts the phase 180 and an inverting amplifier is required to provide another 180 phase shift so that the rise no net phase shift is illustrated in Figure 1.4. Figure 1.4. Experiment No. 1. Implementation of RF oscillators. Page 4. Conditions for oscillation. Two conditions, illustrated in Figure 1.5, are required for a sustained state of oscillation. A. The phase shift around the feedback loop must be effectively 0. E. Their voltage gain, ACL, around a closed feedback loop gain, must be equal to 1 unity. Figure 1.5, general conditions to sustain oscillations. The voltage gain around the closed feedback loop, ACL, is the product of the amplifier gain, AV, and the attenuation, B, of the feedback circuit. ACL equals AV asterisk B, 1.1. I for sinusoidal wave is the desired output. A loop gain greater than 1 will rapidly cause the output to saturate at both peaks of the waveform, producing unacceptable distortion. To avoid this, some form of gain control must be used to keep the loop gain at exactly 1 once oscillations have started. For example, if the attenuation of the feedback circuit is 0.01, the amplifier must have a gain of exactly 100 to overcome this attenuation and must not create unacceptable distortion. 0.01 asterisk 100 equals 1. An amplifier gain greater than 100 will cause the oscillator to limit both peaks of the waveform. Startup conditions. Now, let us examine the requirements for the oscillation to start when the DC supply voltage is first turned on. As you know, the unity gain condition must be met for oscillation to be sustained. For oscillation to begin, the voltage gain around the positive feedback loop must be greater than 1 so that the amplitude of the output can build up to a desired level. The gain must then decrease to 1 so that the output stays at the desired level and oscillation is sustained. The voltage gain conditions for both starting and sustaining oscillation are illustrated. Experiment No. 1. Implementation of RF oscillators, page 5 in Figure 1.6.AQUESTIONTHATNORMALLYARISESISTHIS. If the oscillator is initially off and there is no output voltage, how does a feedback signal originate to start the positive feedback build-up process? Initially, a small positive feedback voltage develops from thermally produced broadband noise in the resistors or other components, or from power supply turn-on transients. The feedback circuit permits only a voltage with a frequency equal to the selected oscillation frequency to appear in phase on the amplifier's input. This initial feedback voltage is amplified and continually reinforced, resulting in a build-up of the output voltage as previously discussed. Figure 1.6. Oscillators with LC feedback circuits. All thought are RC feedback oscillators, particularly the Wien-Bridge, are generally suitable for frequencies up to about 1 MHz. LC feedback elements are normally used in oscillators that require higher frequencies of oscillation. In addition, because of the frequency limitation, lower unity gain frequency, off-must op-amps, discrete transistors BJ Torfet, are often used as the gain element in LC oscillators. LC feedback oscillators include Colpitts, Hartley and crystal-controlled oscillators, etc. In the lab session, we will design and implement Colpitts and Hartley oscillators. Experiment No. 1. Implementation of RF oscillators, page 6. Part 1. Colpitts oscillator. This type of oscillator uses an LC circuit in the feedback loop to provide a necessary phase shift and to act as a sonant filter that passes only the desired frequency of oscillation. The circuit diagram of Colpitts oscillator is shown in Figure 1.7. CAPACITORC1, C2 and inductor L forms the tank circuit. Figure 1.7. RCI is the collector resistor while the emitter resistor, Re, forms the stabilizing network. Further, the resistors, R1 and R2, form the voltage divider bias network for the transistor in common emitter C configuration, while the capacitors C3 and C4 act as decoupling capacitors. The emitter capacitor, CE, is the bypass capacitor used to bypass the amplified AC signals. The emitter terminal of the transistor is effectively connected at the junction of the two capacitors, C1 and C2, which are connected in series and act as a simple voltage divider when the power supply is firstly applied. Capacitors C1 and C2 charge up and then discharge through inductor L. The oscillations across the capacitors are applied to the base emitter junction and appear in the amplified at the collector output. The configuration of the transistor amplifier is common emitter with output signal 180 Ω out of phase with respect to the input signal. The additional 180 Ω phase shift required for oscillation is achieved by the fact that there two capacitors, C1 and C2, are reconnected together in series but in parallel with the inductive coil, resulting in overall phase shift of the circuit being 0 or 360 Ω by changing the values of Experiment No. 1. Implementation of RF oscillators, page 7. Capacitors, C1 and C2, we can adjust the amount of feedback voltage returned to the tank circuit. However, large amounts of feedback may cause the output sine wave to become distorted, while Small amounts of feedback may not allow the circuit to oscillate. The approximate frequency of oscillation is the resonant frequency of the LC circuit and is established by the values of C1, C2, and L according to this familiar formula, FR equals Hlt square root Pwag Spoj Pwalb 1.2, where CT is the total capacitance because the capacitors effectively appear in series around the tank circuit. The total capacitance CT is CT equals Poj 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 plus Poj 1.3. Conditions for oscillation and startup. The attenuation B of the resonant feedback circuit in the Colpitts oscillator is determined by the values of C1 and C2. Figure 1.8 shows that the circulating tank current is through both C1 and C2, the are effectively in series. The voltage developed across C2 is the oscillator's output voltage of UT, and the voltage developed across C1 is the feedback voltage VFA is indicated. The expression for the attenuation B is Punch Pol Hiab Pol Pupayolp 1.4 B equals Pwapad Pyolp equals Pad Pyolp equals Punch Pwapad Pyolp Pwak Pwak Pad Pyolp Hiab Pol Pupayolp. Cancelling the Hiab Pol Pu terms gives 1.5 B equals Poj Poj. As you know, a condition for oscillation is Avastask B equals 1 gives Poj. Av equals Poj 1.6. Figure 1.8. Experiment No. 1. Implementation of RF oscillators. Page 8, where AV is the voltage gain of the amplifier, which is represented by the triangle in figure 1.8. With this condition met, AVB equals C1, C2, asterisk, C2, C1 equals 1, actually, for the oscillator to be self starting, AVB must be greater than 1, that is AVB greater than 1, therefore, the voltage gain must be made slightly greater than C1, C2. Poj. AV greater than 1.7. Poj. Procedure. A. Construct the circuit of figure 1.7 Colpitts oscillator on the breadboard and energize it. B. Record the theoretical value of frequency for the output signal. Fr. Calculated equals C. Observe the output signal using oscilloscope. Measure and record its frequency. Fr. Measured equals E. Draw the oscilloscope waveform on figure 1.9. Figure 1.9. E. Compare the theoretical and measured values of output frequency of Colpitts oscillator and comment. Experiment No. 1. Implementation of RF oscillators. Page 9. Part 2. Hartley oscillator. The Hartley oscillator is similar to the Colpitts except that the feedback circuit consists of two series inductors and a parallel capacitor as shown in figure 1.10. Figure 1.10 inductor L1, L2 and capacitor C1 forms the tank circuit. When power supply is switched on, the transistor starts to conduct, leading to an increase in the collector current, IC, which charges the capacitor, C1, on acquiring the maximum charge feasible. C1 starts to discharge via the inductors L1 and L2. This charging and discharging cycles result in the damped oscillations in the tank circuit. The oscillation produced in the tank circuit is fed back to the base of Q1 and it appears in the amplified form across the collector and emitter of the transistor, the output voltage of the transistor. Voltage across collector and emitter will be in phase with the voltage across inductor L2. Since the junction of two inductors is grounded, the voltage across L1 will be 180 degrees out of phase with respect to the voltage across L2. The voltage across L1 is actually fed back to the base of Q1. From this, we can see that the feedback voltage is 180 degrees out of phase with the transistor, and the transistor itself will create another 180 degrees phase difference. Therefore, the total phase difference between input and output is 360 degrees, and it is a very important condition for creating sustained oscillations. Experiment No. 1. Implementation of RF oscillators. Page 10. The frequency of oscillation is determined as FR equals Hlt square root Pwag Pwalb Poj 1.8, where lieutenant equals L1 plus L2. The inductors L1 and L2 act in a role similar to C1 and C2 in the Colpitts to determine the attenuation B of the feedback circuit. 1.9. B Pwags Pwags. To assure startup of oscillation, atmosphere greater than 1 B. Pwags. Av. Pwags 1.10. Procedure. A. Construct the circuit of figure 1.10 Hartley oscillator on the breadboard and energize it. B. Record the theoretical value of frequency for the output signal. Fr. Calculated equals C. Observe the output signal using oscilloscope. Measure and record its frequency. Fr. Measured equals E. Draw the oscilloscope waveform on figure 1.11. Figure 1.11e. Compare the theoretical and measured values of output frequency of Hartley oscillator and comment. Experiment No. 1. Implementation of RF oscillators. Page 11. Part 3 to 555 time Rasen oscillator. The 555 oscillator is a type of relaxation oscillator for generating stabilized square waveform of various frequencies up to 500 kHz with different duty cycles, a 555 timer. Connected to operate in the astable mode as a free-running relaxation oscillator, astable. Multivibrator, ISHAN and figure 1.12, their threshold input, THR, is connected to the trigger input, TRI. The external components R1, R2 and KEXT form the timing circuit that sets the frequency of oscillation. The 0.01 UF capacitor, C1, connected to the control, CON, input is strictly for decoupling and has no effect on the operation. Figure 1.12. The 555 timer consists basically of two comparators, a flip-flop, a discharge transistor, and a resistive voltage divider, as shown in figure 1.13, initially, when the power is turned on. The capacitor, KEXT, is uncharged and thus the trigger voltage, pin 2, is at 0 volts. This causes the output of the lower comparator to be high and the output of the upper comparator to be low, forcing the output of the flip-flop, and thus the base of Q low and keeping the transistor off. Now, KEXT begins charging through R1 and as indicated in figure 1.13, when the capacitor voltage reaches 1/3 VCC, the lower comparator switches to its low output state, and when the capacitor voltage reaches 2/3 VCC, the upper comparator switches to its high output state. This resets the flip-flop, causes the base of QD to go high, and turns on the transistor. This sequence creates a discharge path for the capacitor through R2 and the transistor, as indicated. The capacitor now beban to discharge, causing the upper comparator to go low at the point. Experiment 0.1, implementation of RF oscillators, page 12, where the capacitor discharges down to 1/3 VCC, the lower comparator switches high, setting the flip-flop, which makes the base of QD low and turns off the transistor. Another charging cycle begins, and the entire process repeats. The result is a rectangular wave output whose duty cycle depends on the values of R1 and R2. Figure 1.13. The frequency of oscillation is given by equation 1.11, Fr equals Prog plus Prog, Poj 1.11. By selecting R1 and R2, the duty cycle of the output can be adjusted. Since KEXT charges through R1 plus R2 and discharges only through R2, duty cycles approaching a minimum of 50% can be achieved if R2 greater than R1. So that the charging and discharging times are approximately equal, a formula to calculate the duty cycle is developed as follows. The time that the output is high, th, so long it takes KEXT to charge from 1/3 VCC to 2/3 VCC, it is expressed as th equals Prog plus Prog, Poj 1.12. The time that the output is low, th, so long it takes KEXT to discharge from 2/3 VCC to 1/3 VCC, it is expressed as TL equals Prog 1.13. Experiment 0.1, implementation of RF oscillators, page 13. The period t of the output wave for Mr. Zoom off to handle the following formula for tist reciprocal off in equation 1.11, 1.14. T equals th plus TL equals Prog plus Prog, Poj 1.12. Finally, the percent duty cycle is 1.15 duty Prog Pios cycle equals 100% Pugs Prog Pios plus Prog Pike. 1.16 duty cycle equals Pug plus Pug 100% Pug plus Pug. Keynotes. To achieve duty cycles of less than 50%, the circuit in figure 1.12 can be modified so that KEXT charges through only R1 and discharges through R2. This is achieved with a diode D1 plus as shown in figure 1.14. Figure 1.14. The duty cycle can be made less than 50% by making R1 less than R2. Under this condition, the formulas for the frequency and percent duty cycle are, assuming an ideal diode, Fr equals Prog plus Prog, Poj 1.17 duty Pug cycle equals 100% Pug plus Pug 1.18. Experiment 0.1, implementation of RF oscillators, page 14. Procedure. A. Construct the circuit of figure 1.12 555 oscillator on the breadboard and energize it. B. Record the theoretical value of frequency for the output signal. Fr calculated equals C. Observe at the output signal using oscilloscope, measure and record its frequency. Fr measured equals E. Draw the oscilloscope waveform on figure 1.15. Figure 1.15. E. Compare the theoretical and measured values of output frequency of the oscillator and comment. Experiment No.1. Implementation of RF oscillators, page 15.